that at the end of the day we have some time for discussions. So the idea is that like more specific questions or things that are taking too much, we can move to this end of the day. Also, the idea of the workshop is to have this cross-fertilization of ideas from different topics. So it would be nice that, also if we can get together people from different communities to talk to each other, right? And not just so that usually talk to each other. Okay, and with that, I welcome our first speaker, Rina.
Good morning, everyone. You hear me? I think I hear myself. Okay. My plan today is to talk about and/or search spaces and how they are being used for anytime algorithms as the center of anytime algorithms for probabilistic reasoning. And here I have my collaborators. How do I point? Well, I can just, you see them. So these are just a sub-list of collaborators in recent years. This is work that is ongoing for almost 20 years. And I will just give sort of an overview of the work that is related to and/or search spaces. So this is my plan. I will start by commenting about the relationships between and/or search spaces and arithmetic circuits, give a small overview of and/or search spaces, and touch about compilation and/or multi-valued decision diagrams, and how we are using, rather than doing compilation, we are using this as the basis of solving problems in a timely fashion, not exactly, approximately. And then if we have time, I will talk about our recent work on abstraction sampling and the rest of the work. So let me start. Here is an example of a very simple Bayesian network at the top. And on the left, you see an and/or search tree that captures the same probability distribution that the Bayesian network is capturing. And on the right, you have the arithmetic circuit. You can see the structure is very similar. Syntactically, the main difference is that in arithmetic circuits, the parameters are at the leaves, and in and/or search graphs, like in decision trees also, they are on the arcs. In more details, if we want to look at them side by side, so basically they are isomorphic. Under some condition over arithmetic circuits, you can move from one to the other, especially if the starting point is the Bayesian network or the graphical model. You have pseudo trees that guide and/or search trees, as I will describe. D trees are used for arithmetic circuits, but the main focus that I already articulated is how do we use them. So compilation is the main focus of the arithmetic circuits community, and anytime heuristic search algorithm is the other focus that I will describe today. The input is also sometimes different. If you can start from a full graphical models and then move to one or to this representation, or you can start from, in the case of arithmetic circuits, from the circuits and learn the parameters. So we have these two types of initial starting points. And arithmetic circuits exploit naturally very well by compilation the logical structure, the local structure of the functions. In the case of and/or search, you can or you may not use it depending on your methods. Another maybe difference is that the focus often is on bivalued variables. In the case of arithmetic circuits, maybe not always. The focus is on multi-valued variables, and representation is a table often. So that's the main difference, or actually the point is that there is not much difference. And I will go and talk from now on, and I'll describe the work that uses anytime algorithms with this structure. So we are talking about graphical models, the starting point. These are examples, very well-known example, just to show you are familiar with this, I assume. Protein folding design or redesign is one of the focus of our work in recent years, but I will not have time to talk about it. What we want to start is from the formal definition. What are the graphical models? variables, domains, and a collection of functions that represent some probability distribution or some cost function. And they can be abstracted into a graph, primal graph, where each variable is a node, and you connect two nodes if they appear in the same function. And this structure allows us to really, it captures conditional independencies that exist in the probability distribution and can be exploited very well. And what we want is to solve all these problems here, max inference, map, sum inference, weighted counting, partition function, mixed inference, the marginal map, when we have both summation and maximization on top of the product, and also an influence diagram. Here is a picture of the influence diagram. And the difficulty of this problem is getting harder as we go from top to bottom. They are all hard. And the philosophy is we cannot solve this problem exactly most of the time, but we can explore the exact solution. Let's try to have algorithms that with time will get better and better solutions. And eventually they have to get the exact solution if you give them all the resources. And also let's try to generate bounds. Whenever we stop, we want to have a bound on the exact solution that we have. So that's the picture. And this is an overview slide of the approach that we have taken. The approach is the approach of heuristic search. So we do want to find a unifying method that is anytime, as I said. And what I will argue is that heuristic search is a perfect framework for this type of algorithms. And what you see here is a search space. You see here a search space, and you need a heuristic. And I will show that we have the capability of compile heuristics, but take them to the next step and use them within search, and the search will be over end or search spaces. So let's start from to see what end or search spaces are for the probabilistic graphical models. Okay, so you have here at the top, you have a graphical model, and you can immediately see that you can generate a pseudo tree that captures conditional independencies in it. If you assign a value to A and B, these two subproblems are independent. So instead of laying all the configuration, all the assignments of values, or values to a variables in a tree, in a simple tree, we can try to exploit the structure of the problem in the search space. We know that we can exploit the structure of problem in algorithms such as variable elimination, bucket elimination. This is immediate, but those algorithms don't lend themselves into anytime behavior. You can solve the problem if the induced width or tree width is small, otherwise you cannot. Memory prohibit that. But search is more flexible, so we want to exploit the structure, and we can, instead of thinking about this tree, we can have this AND OR tree. In this AND OR tree, once we assign A and B a value, these two subproblems are decomposed into two subtrees, and this is an AND node. Let's solve this problem and this problem independently given the assignment editor. So you have a layer of what we depict here is the name of the variable, we call it an OR node, it has the values, and the assignment node is an AND node. It may root several problems that all can be solved independently, and this is guided by the pseudo tree of the problem. And here a solution is a path, here is a solution is a subtree. There is another property that we exploit that is just based on the graph. We know that often in search trees, there are several subtrees that are identical. It's often hard to recognize them in advance, but the graph allows us to do that. In this example, we can see that the subproblems below D and F probably depends only on the value of D and F. So instead of having this AND or search tree, we can recognize that actually this is AND or graph, because all these subtrees are the same. And this can be also discovered just by looking at the graph and looking at notions such as context that I will describe immediately. So to summarize, the main thing is that we are starting from a graphical model, and instead we can consider the tree, the OR search tree. But if we have the pseudo tree, and we can always generate it, the pseudo tree is just a tree spanning the graph that don't have arcs going between branches. Then we can have the AND/OR tree. It will have less nodes, captures the same probability, the same set of configurations. And we can also have the notion of context that tells us that a variable is independent given the context from the rest of the problem. For instance, the context of L is just AE because A is separated from the rest of the problem. So based on context, we can move trees to graphs. We can do it for the OR trees, and we can do it for the AND/OR trees. And the number of nodes will decrease. And you can see that here in this structure that we call context minimal AND/OR graph, we get the smallest representation. And this is just based on the graph. And we can also characterize the graph parameters that govern this. So the height of the pseudo tree characterize the size of the AND/OR tree. It will be exponential in the height. The induced width or tree width will characterize the size of the context minimal AND/OR graph. The path width will characterize the size of the OR tree. And we can also generate those in that amount of time. So once we have this realization, we have the spectrum of trees, and we can solve any of the queries that we are interested in over such, or define them over this tree, and address the question of algorithms to answer those queries. Please ask questions if you have any questions during the talk. So this was just the graph, but we have its knowledge base, its information. We have to have the parameters. We sprinkle the parameters on the arcs from the tables, and we can capture the whole probability distribution, the weights that we have on the tree. The product will be the product of the configuration. So this is just captures the same probability distribution. And now we can try to explore the search tree or to define on it the task that we are interested in. So for example, if we are interested in the probability of evidence, we can define the notion of a value. The value will be the probability of evidence below each node, and we can recursively from leaves to node using product for end nodes and summation for OR nodes. At the same way that it's done in arithmetic circuit, we can just propagate the information to the root and compute what we want in the case of summation query, in the case of optimization query, and we can do it on the AND/OR tree, and we can do it on the AND/OR graph as well. And in the case, what we will see that when we are doing it in the case of AND/OR graph, we will need to cache some information for the search algorithm. Now it depends. I mean, we can have many pseudo trees, and the questions of what is a good pseudo tree was explored. This is just to illustrate that for this problem graph here, you can have this pseudo tree or this pseudo tree, and this parameter, tree width and height, are different in them, and it's not so clear which of these AND/OR search graphs that this dictates would be superior. If you can cache information, you want the tree width to be small. If you decide of a linear memory, you want the height to be small. And this, it's not possible to have both parameters optimized on the same pseudo tree. So that was my introduction of AND/OR search graphs. I think many of you are familiar with that. We also did use it for compilation. We explored the possibility of starting from an AND/OR context minimal graph, compile it in the same nature that you do with OBDs, and we developed this notion of AND/OR multi-value decision diagram, and we're able to show, here is a tree, here is a context minimal graph, and we can compact it to the minimal and or multivariate decision diagram. And the thinking is, first of all, compilation obviously in some cases would give you a lot because you put the circuit, the graph in memory, but we thought that this will help us generate better heuristic, as I will show, and it can help. But I will not talk about this work anymore. I will focus, as I said, on how to now use the end of search graphs for anytime algorithms. So we want to use the search graph, the search tree that we have as an implicit structure that we explore, not as an explicit structure, and we explore it, if it's heuristic search, with the aid of heuristics. So in heuristic search, for each, if you are computing an optimization, you are trying to have a lower bound for each node of the optimal solution, or in the case of summation, the lower bound on the count. And the question is, how do you get this heuristic? And it turns out that we can get it also from the graphical model by compilation, by doing these algorithms that I mentioned at the start, like bucket elimination, which can be perceived as a compilation algorithm, but we cannot do it exactly. We will do it approximately using a method that is called mini bucket. So what is the idea? You have the functions and the input function, and you are sending messages from one variable by variable elimination. You can bound the size of the message by partitioning and not sending a full message on all the functions, but just smaller functions. And you can control the size of the function by a parameter like an I bound that says how big would be the message that you are sending. And the nice thing about this method that is guaranteed to give you an upper bound or a lower bound, and it's a perfect candidate for generating it from heuristics. So this is basically what we did as a start, and we also are able to improve it by notions such as cost shifting between buckets. These are well-known methods in variational community, and also for summation summation queries, we had the power algorithm, and this leads to what we call weighted mini bucket. So here is, this picture is again, the high-level view that you may see again a few times of the methodology that we are using. You have the search tree, and we use the mini bucket heuristic to generate, before we start to solve the problem, we are compiling these functions, and they are standing there and can be used when we are doing the search. And so now that we have the two components that we need, the search space and the heuristic, we can now tap into all the literature of heuristic search over the last 50 years. And best first search, the type of search, best first, depth first, and recursive search. And I will point on some of these methods in the next slide. But this is a very valuable resources that we simply took and imported it to our domain. Here is so what I will do now, I will just show a little bit of our search, of our methods in a very high level manner to really illuminate more what we have done. This is for solving map problem, just to stress that we are not, rather than compile the AND/OR tree, we have this structure. It implies an implicit AND/OR search graph, and we are exploring it here in a depth-first manner. And you can see only part of the problem is given. And again, this is the same story that I said before. And what I want to talk about now is to focus on one of these tasks that is the most difficult. We heard about it yesterday, the marginal map. So our work started from map and moved to marginal map and summation queries and to influence diagram. And marginal map is known to be one of the most difficult queries, because you have here in this graph, you have variables that you want to optimize and variables that you need to sum over, which dictate how the pseudo tree, it restricts the set of pseudo trees that you can use and make cause trees not to be trees, as we saw in the example yesterday. And now this is the end-or graph. It will also have the maximization variables at the top, summation variables at the bottom, but this is again implicit. We are not generating this graph a priori. We are searching it, hoping to search only a small portion of it with the aid of the heuristics that will also be generated for this task, and that would be the process. So we now have the ingredient of doing heuristic search, and a lot of the work we have done since is to go and think how we can generate anytime algorithms, namely provide an answer immediately if necessary with bound, but continue and have better and better solutions. And one of the ideas from heuristic search is to use weighted heuristic, which in this case will be able to provide you a priori, you know what would be the upper bound. We use ideas such as restarts, recursive search, and combinations. We also use ideas of best first and depth first search, interleaving them. One is generating an upper bound, one is generating a lower bound, and doing it in a variety of sophisticated ways, using look-ahead methods, alternating, and so on. So all this is easy to say fast, but it requires significant work and an empirical evaluation to see what is working. The results that we show are empirical. We have a collection of benchmarks, the UAI benchmarks, and we run the variety of algorithms that are candidates that we develop on these benchmarks and plot the results. And the main thing is to show how these are just 3 instances from of the benchmarks, and these are problems that is hard to solve exactly. And you can see that the feature that we would like to emphasize is the fact that with time, the bounds, you have an upper bound and lower bound, the same color is the same algorithm that provide both, and we are trying to see which one is doing best on which problem. And we can also play, we have the strength of the heuristic is one of the components. This is an example of work from weighted counting. Partition function is a very difficult task. Normally, you cannot solve it exactly. And we develop on the same methodology, the and/or search with the heuristic now for this task. We developed algorithm that will, again, provide us with this anytime behavior. And we explore different versions, trying to come up with the best one, or to see under what condition, which algorithm is better. So I will not go into more details on this, on the details of this work. I will just mention it in the last many years. We developed this class of algorithms. These are student theses that are focusing on heuristic search, but also sampling to talk about summation tasks. And I think some of my slides were commented. I had some slides that are not showing, but never mind. That's fine. But that's what I would like just to share, that these are the, several theses that we have with the students. Some of them are mentioned at the beginning, some of them not. We mentioned at the end. So if you are interested, you can go there. And one of the ways we evaluate the work is using the UAI competition. So UAI competition started in 2006. We have also 2 competitions since 2014 and 2016. It's not here, and 2022 that I will comment at the end. And we were able to show, comparing with other people who have developed algorithms in any time manner, we are able to show that algorithms are pretty strong. And you can find the software of all the algorithms that we are developing in my software page. If there are any questions, you can ask. Okay. I have 10 more minutes, and what I would like to do now is to focus on, to share with you some recent work, more recent work that we are doing now that is focusing on sampling. Okay. So search is definitely valuable, and you can stop the search at any time. But if you want to solve summation queries, sampling is the natural approach. And one of the questions is how to sample the search space and exploit structure, namely how to sample the end of search space or exploit the structure. We have some work, two types of work that we explored. One is called end or sampling that I'm not going to talk about. This is work of Gugat. And this is the more recent work that we call abstraction sampling, where we are trying to control, to do the level of sampling and searching that we are doing using the notion of abstraction. So overall, the idea is that if we are sampling, as you know, we are normally, if this is a search tree, normally it's common to do importance sampling to estimate the partition function. And it will, importance sampling generate just configuration, and some of them take the average as an estimate. Instead, we would like to consider sampling the subtree of the problem, not just a path, but sampling a subtree. So instead of sampling this structure, we can sample this subtree to configuration in it and provide an estimate, or we can take it further and estimate a larger subtree, a collection of them, and take the average. So this picture gives us a transition. On the left, we are just doing only sampling. If we take it all the way, we will do only search, and we will search once. But we would like to explore the potential of doing something in between and improving sampling.
So,
now, yeah.
What do these colors represent? Maybe I'm missing yellow and blue.
This is, so I will describe, maybe it will be clear in a minute. So this idea is coming from work by Knut and Chen, his student Chen, on estimating search space sizes. So, Knut introduced this sampling approach to estimate the size of a vectoric search tree if you're trying to solve a constraint satisfaction problem. And it was taken later by heuristic search people to estimate the search space when you are using your heuristic search algorithm in advance, because you don't know when you start to solve a problem what will be the search space. So we took it further, and this is for summation query. We took it further to the idea of estimating the partition function. What is the idea? The idea is to subdivide the search tree into parts and to generate one sample from each part. So you are generating a tree. Instead, so we subdivide the space into parts, enumerate over parts, and sample within a part. We call each sampled subtree a probe. And it resembles the notion of stratified sampling. In stratified sampling, we know the idea is to divide sample from each strata, and it can be proved that it reduces the variance. So Rizzo proved that if you are moving from regular importance sampling to stratified importance sampling, you can reduce the variance by the number of stratas, number of elements of stratas that you have, and the variance in between the stratas. So this, what we are doing is similar, and I will show you an example. I think it will be easiest with an example, but the idea is to have an abstraction function or type from the configuration in the trees to a subset of integers, and then at each layer in the search tree, we divide it into this abstract states, and we sample from each one of them, and this is how we generate a subtree. So here is just an illustration, and it's an illustration on the OR tree. So here is a tree. We can start by generating the tree, and we will use for this example the value of a of a node as the abstract state. So if we have several nodes with 0, they will be the same abstract state. So the first level, we have only one node. In the second level, we have B equals 0 here and here. This is the same state. So stochastically, we choose one of them and remove the other. So we will have, at the end of this level, we will have just these two nodes, and we continue. Another abstraction, we stochastically select one, and that's the end of our sampled subtree, and we can estimate it. It's a subtree. One thing I forgot to really point is that as we do that, we change the weight associated with each node, because now it captures more information. At the end here, we have each configuration capture 4 paths, and accordingly, we do this would be our estimate here, and we can do it many times, and we can take the average. This is the method. Here is an illustration of how we extended it to AND or search trees. So on the left, you have an AND or search tree, full one, and on the right is an example of a sampled tree that we create, and we take the average when we are doing the computation. It turned out to be a little bit technically difficult to move this idea to AND or tree and to remain in an unbiased state. And we developed a method that explore the pseudo tree in a depth-first manner that I will just illustrate here. As you can see, at the end I have two nodes and we remove one of them. It's all done stochastically with a proposal function, and this would be one probe. And so here is the AND or search tree. This is what we sampled, and we do it again and again with the aid of a proposal to decide which element will be selected in each strata. And you can see here the heuristic. So the heuristic, that is again the weighted mini bucket, will be a component in our proposal. I will not get into how we are doing it. It works for any proposal, but a good one would help. And that's the method. We can control the size of a probe because we can control how many abstract states we have, which is n, and we have n variables, so each probe will be bounded, and we can prove that it's unbiased. And the hope or the claim is that the variance is smaller if we are doing it that way, because a search tree is just a collection of configuration. We have to show that doing it in a controlled way in a tree is better than just this configuration, doing this within a tree. So the main question, of course, is the abstraction function. What is it? And we developed two types of abstraction function. One is based on the context. We know that if the context is the same, the two subtrees are identical, and it will be exact to pull together all these states that have the same context into one abstract state. But we would have too many abstract states, and we didn't do anything. But we can relax the constants, select a subset of variables to partition, and we can also randomize and select a hash function over the context. These are two of the main abstractions that we use that are based on the context. And then recently we worked with heuristic, using the heuristic as a basis for abstraction. And the main question is which abstraction class is best, what granularity to use. And so far we experimented with it on all these benchmarks that we use. And here I'm showing just one graph on one problem, a recent one, where we also illustrate the difficulty of work with approximation and anytime algorithm. You can illustrate the power of this method only on hard problems. And on hard problems, you don't know what is the exact answer. So in this work, what we did is we ran this algorithm many hours to get a baseline that we propose, since it's unbiased, that it represents sort of the exact answer. And what we see is that all these many variation of this algorithm with different abstractions, with different granularity of the abstractions, operate as a function of time. And the one in this example and that is based on the heuristics was best. Not uniformly, but overall it was showed good performance. So I wanted to share this. This is the bottom line, the current status of this and/or search approach for weighted counting. Yeah, we still have a lot to explore. And I promised to say something about the UAI competition. We recently revived the UAI competition in 2022, and we hope to continue this. And this is just an illustration from the webpage. You can look at the webpage. The abstraction we compare against 3 other approaches. This is the results. This is the higher is better. In this, we show performance at different time steps, and this is completely aggregation of all these instances. So abstraction sampling in this case didn't appear to inferior overall to some of these methods. In our experiments, we showed better performance in general, but one of the points is that all these UAI instances are easy because we have to have the exact answer, and we can. Most of these problems are solving those the problem exactly because it's possible. So, but anyway, my point here is to advocate and really invite people to participate. And maybe this is something that we can talk in the discussion. Just occurred to me right now. Moving forward, we are learning. We have some work on learning the abstraction function. And I think what drives us forward is neurosymbolic algorithm, doing some neural network within our algorithms and applying everything to causal reasoning. Thank you. I have one more slide. This one. So here is the main contributors and all my students and my book that was the new edition is from 2019, focusing only on exact algorithm. I hope to one day extend to approximations. Thank you.
Okay, so we have time for one quick question. Yeah.
Okay, you mentioned that when you do sampling, you lose the any time. You don't have the bounds, no? Because
Okay.
maybe you can compute like confidence intervals or something like that.
Okay. So there were 2 slides or 3 slides that I commented by mistake. I think I went back and forth. I wasn't sure how much time I would have, and this was on this problem. There is also a class of sampling algorithms that have probabilistic bounds. A weighted mini-bucket importance sampling that we used also in the new generation of the marginal map approach algorithms. We are not solving the summation subproblem exactly. The first generation, the summation subproblem is chosen so that it can be solved. The problems that we are illustrating over were exact, but if we cannot solve the summation subproblem exactly, we use sampling. We use weighted mini-bucket importance sampling that provide upper and lower bound probabilistic bound. So this is the main way that we exploit sampling into this search. But abstraction sampling doesn't have that, cannot be accompanied with bounds, abstraction sampling, because a variety of things. But yes, it's very important to really to continue and have this bound, and you can do that with some sampling scale. What happens is when you take up a weighted mini-bucket importance sampling that is geared to provide good bounds, probabilistic bounds, and compare it with regular importance sampling with any function, it appears to be inferior. But you don't know this a priori. A posteriori, you see that these other methods just give better answers. There is an additional work on sampling, that I mentioned, the partition function. All the work on partition function, providing upper and lower bound, is based on sampling. I just didn't talk about it. I mean, you explore part of the search, you sample the rest with weighted minimum important sampling, and you get this upper and lower bound. And there are a variety of trade-offs explored in that work. And the work that is sort of the superior one is dynamic importance sampling. So if you want to look at this work for partition function, dynamic importance sampling would be the key, where you are trying to decide whether to expand search or sample in a dynamic fashion based on some statistics.
Okay, so just to keep with our schedule, maybe we can take other questions offline in the break. So